history on me. So my name is Chris Greer. I work for a company called Packet Pioneer. I do Wireshark training. I do consulting. People send trace files, try to help them get an answer to their problem. When I'm not doing things like that, you can find me blogging, speaking at different things like SharkFest, and just trying to help people make sense of packet captures. Now, I know packet captures can be pretty daunting. It can be confusing, especially when we're getting started. So the way that I teach, I try to give you as much hands-on as possible because that's how most of us learned how to do this, right? Now, one of the common things, or one of the biggest complaints that I get called into is troubleshooting slow networks. So when's the last time your users called you up and said the network's running too fast, right? I don't typically get that call too much. Well, thankfully, because I can still, make money and, put food on the table. But we're going to talk about troubleshooting slow networks in this session. Now, if you were in the pre-conference class, this is exactly the point that basically we left off at. If you weren't in the pre-conference class, no worries, as long as you've attended some of the other sessions about doing some basic TCP filtering and looking at TCP conversations from more than one point, maybe using some of the TCP stream graphs. So if you have a handle on some of those functions, then that's exactly where we're going to be picking up. This topic, again, no doubt many of you are here because you are blamed for slowness on a network, right? So there's a performance problem, people are getting spinny wheels, the progress bar isn't coming across as fast as they expect it to because you just installed some new amazing 10 gig link across the ocean and people are expecting, you go from 1 gig to 10 gigs, so we should get 10 times the performance, right? Well, then something goes wrong and of course they blame you, they blame the network. Well, so in this session, we're just going to talk about the approach to troubleshooting some of those things, and specifically when the problem is TCP related, when it's not the network, and how we can look into different facets of TCP and not just improve performance, but really get to the bottom line of why things are slow. All right? So that's why we're here today. Now, like we just mentioned, slow. Why are we still talking about slow? You would think by 2019 we would have this problem licked, Here we are, we're facing 2020. But still, slow is something that we battle. Not just disconnects and application drops, but slowness, performance problems. And this is in a day and age where we have fiber running everywhere. We have links that are 1, 10, 40, 100 gig connections and beyond. So really, when it comes to capacity and bandwidth, we have more than we ever have had before, but things are still slow. So we're going to talk about why that is in a lot of cases. Of course, we can't cover everything in an hour and a half, but there's some key things that we can look for, especially when we're doing file transfers that can help us to get to root cause. Now, just because, one thing I want to just kind of hit right off the bat is when we're installing new connections and expanding out the network, something we really want to make sure that we do just from the get-go, especially if we're coming from the network side of the house, is that we validate that we're getting what we're paying for. You want to make sure to validate your network. The last few times I've worked with people doing slow file transfers and having problems in those types of environments, it really resolving the problem didn't come down to packets. Resolving the problem came down to a few different iPerf sessions, and we were able to find the device that was dropping packets. Had we just started with iPerf and validated the network from the beginning, then we may have found that link a little easier than digging through packets first. So make sure, it doesn't necessarily have to be iPerf, which is an open source throughput tool. Throughput test your network. Just do it. Make sure that you know the capacity, the bandwidth of your connections, especially if it's a new environment, a new area of your network that you're bringing up. Make sure to test it. Don't assume that you can plug in a link, see a light go on, and that just because you see a 10 gig light, that means you're getting 10 gig, okay? make sure to stress test your network. Now that's a whole conversation as far as tools and how to do that, and there's hardware analyzers that do it. There's, obviously I mentioned iPerf is one, but definitely something that we want to make sure that we do. Okay, that's just from the get-go, just as network engineers. Because when we're approaching things from a packet level, it can take a long time to get these packets, to open up these trace files, to understand them, to look at TCP conversations, look at these TCP graphs, only to find out that we just had some packet loss on a link. We probably could have found that another way, right? So let's make sure to test the speeds and feeds, the highways and byways, and validate that we are getting the kind of bandwidth and throughput that we expect to get, okay? That's just as network engineers, best practice. Now, what are things that cause networks to be slow? We're really going to focus or talk generally about these 3 points today. So packet loss or congestion, those two can go hand in hand. TCP protocol behavior, we're definitely going to spend time there. And toward the end, if we have some time, I'm going to show you some examples of chatty applications. Now, packet loss and congestion. Hopefully as network people, we have a good idea what that means, right? So literally losing packets on a link somewhere along a path between A and B. Congestion, traffic increasing on a certain link at a certain period of the point in time during the day and affecting the other competing traffic for that link. The TCP protocol behavior, like I mentioned, we're going to talk about how TCP works with windowing and how it decides to send or receive and how much should be out on the wire and give you guys some practice there and so on. So let's go ahead and get into it. So first, I just mentioned this. Let's make sure that we are getting what we're paying for. We want to make sure we test our network links. There's one example of an open source tool. We might have to run several sessions of it to really get the throughput that we need to successfully test a link. Sounds simple, but make sure we have a good roadway to then throw packets across. Now, we want to watch for signs of packet loss. The tool itself should tell us, like, hey, I was able to achieve 900 megabits per second out of 1 gig, and I had this percentage of packet loss. All right? Now, what does packet loss look like as we're going across the network? We want to make sure that we have management level access to infrastructure devices along the path, things that we're going to look for, link level errors, FCS, CRC, discards, things like that. In our trace files, we're going to look for retransmissions, dupacks, out of orders, things like that. So that symptom can lead us to looking back to the network and looking for those link level errors. Now, there's definitely tools out there that will tell you, hey, that switch over in that closet on port 3 is having FCS errors. Go look there, right? So hopefully you have some type of network management and monitoring going on that can help you to find those things. But the signs of loss, want to watch those discards, link level errors, and so on. Now, let's actually start having some fun. Now, in a perfect world, when it comes to network performance and behavior, in a perfect world, we have no network limits, no receive limits, and no send limits. This client says, hey, server, I want this file. That file server says, great, here's your file, and there's absolutely no limitations whatsoever. The server can send as fast as it wants. The network can handle all the traffic that is put across it, and the receiver can handle any amount of ingress traffic. There's our perfect world, right? That's when you and I actually start losing our jobs because things are running too well. As we know, this isn't reality, right? The fact of the matter is the network does have limits. The server has a limit on how much it can send. The receiver has a limit on how much it can receive. The question is, which one of these is hurting you? Or is it a combination? That's what I want to teach you how to find in this class, okay? Specifically, if you can walk out and have a good idea how to figure out which one of these 3 is limiting you. This is after you've already stress tested your network and you've patched the holes in the road and you've shaved down all the speed bumps and you've made sure you don't have a lot of discards and errors on your network. But our goal here in this class, we're going to find out which one of these three is really causing our issue. Like we said, the network has limits. Between two endpoints, we could have a very small amount of bandwidth. We could have a large amount of bandwidth. The thing about it is that those two endpoints don't know what's in the middle. Let's start with that concept. If you're a client, I'm a server, you ask me for a file, I pull up that file and I get ready to send it to you. TCP does not know what's in the middle. Right? When I'm first getting started in sending you something, we don't know what's in the middle. That's part of its job. I want to figure out how much can I send you without loss, without causing my own congestion. But at the very beginning, it doesn't know, right? So I'm not going to assume that we have a 10 gig connection with low latency and I can just fire hose traffic across this link, right? What would be some cons to a server doing that? Let's just say a server is 10 gig attached. If you ask me for a file and I literally just blow the doors open on that 10 gig connection as I send you that file, what would be some downsides there that you can think of in your head? What's some downsides to a server just opening up a fire hose and boom, you asked for it, here you go, boom. Go ahead, sir. Okay, what if the fire hose coming in can't successfully fill the 10 gig? What if on the other side of that 10 gig I'm going down from 10 gig to a 1 gig link that's going somewhere else? There's a choke point, right? Any other thoughts? I could have a competition for the link. Yeah, I mean, that server isn't just serving me. It's doing other things with other services with other users, right? So it's not going to say, okay, whole hog, you get the entire network connection, and we're the only ones here, so I'm just going to go ahead and slam this thing and assume that 10 gig is our weakest link. It's not, right? So the server at first doesn't know what kind of link we have between us. So let's go ahead and illustrate this, all right? This whole concept of TCP windows, receive window, congestion window, send limitations, network capacity, okay? And this is one way that I thought of how we could illustrate this. All right, so you have an empty swimming pool. I've got a full swimming pool. And you just asked me for the water, all right? That water obviously would represent our data. What we have between us is 100 feet of 3/4 inch garden hose, all right? 100 feet of 3/4 inch garden hose. Let's start with this number. Let's begin here. How much capacity can that hose handle? If you put your hand on one end, and on the other end, I start pouring water into that hose, how much water do I have to pour in before you feel water come up against your hand? On 100 feet, 3/4 inch hose. Think about that for a minute. Maybe, I don't know if some people are very good at math, could just do that on their head. I actually went out to Mr. Google and he answered that question for me. So 100 feet of 3/4 inch hose holds about 2 gallons of water, all right? That concept makes sense? So right there's our network capacity. Not 3 gallons, not 1 gallon. I can have 2 gallons of water on that hose at once, all right? According to Mr. Google. This could be wrong, so don't go testing it. Don't, take this as gospel here. That seemed to make sense to me. Now, what does that mean? That means, let's just say 2 gallons of, let's use milk jugs because those are for for people who aren't on the gallon system or they're on the metric system, like the rest of the world. So let's just use those two images right there as gallons. So that's our network capacity, all right? Right there is what we have to deal with. Now at the beginning, I don't know that we have two gallons of capacity. I don't know that. All I know is that there's this link between us. I don't know if it's a drinking straw that's really, really long. I don't know if it's a huge city pipe that's you could walk through between us, right? So think a T1 versus 10 gig connection, all right? I don't know which one it is. So we also have something called send and receive windows. Now you guys have heard this. You've probably done some analysis on TCP connections before. Let's just illustrate those real quick. So to fill your pool, you're going to receive water from the hose and you're just going to pour it in the pool. You're going to catch the water in this glass, you're going to pour it in the pool. You can't receive any more than that glass. If a gallon comes out of the hose and into a pint glass, what's going to happen? If a gallon of water comes out of that hose and into a pint glass, what's going to happen? It's going to overflow, right? I can't carry a gallon in a pint glass. I can only carry a pint glass. So it's going to take a while, but I'll take that pint glass, fill it on the hose, and pour it in the pool. Fill it up, pour it in the pool. I can only receive one pint glass at a time. On the sender's end, because there's a pint glass over on that other side, the sender can't send any more than I can receive. He can't go, despite what the network can handle, the sender cannot send more than that pint glass, period, no matter what the network can hold. All right? There's your send window. So whichever of the two of these is the smallest, that controls throughput. So let's just leave this picture alone right now. If we left this picture, didn't change anything, are we making use of the network? Are we fully utilizing our network at this time? Not yet, right? We're only sending a pint glass through it. It can handle 2 gallons. So a lot of the time when we're troubleshooting issues, not all, but when we're troubleshooting slow file transfers, this is something that I want you to start watching for immediately. This is your first symptom. Are we using the network to its capacity? All right? Is TCP, either with the send window or the receive window, not sending what our potential is? We're going to talk about the potential in just a minute here. All right, everybody good there? Questions at this point? So we have send window. This is our capacity we can hold. We're also going to talk about how to calculate that, bandwidth delay product, and our TCP receive window. Okay. Now, not long after a TCP file transfer happens with modern stacks, we start with the pint glass thing. We do this TCP slow start thing, but in many modern applications and modern stacks, we'll say, okay, I was joking about that whole pint glass idea. I'm going to go ahead and really give you something to work with, Mr. Server. Let's increase this to 5 gallons. I can't just grab a single pint glass. I can get 5 gallons from you. Send away. Okay? So it's not uncommon to see, not long after a connection begins, the receiver blow its receive window to the sky and say, you know what? I can handle a ton. Right now, if that's true, the receive window can truly handle that amount of water. Our network would be over-congested to send that much. Everyone agree? The network can't handle that much. However, my client doesn't know yet what the network can do, so it's just saying, hey, go ahead and send me everything you got. So the server's like, all right, you know what? That's cool. I know you can do 5 gallons. I understand. You're awesome. You're a rock star. We still don't know what this network could do, so why don't we just move away from this pint glass thing and let's go to 1 gallon. All right, so I'll go ahead and increase what I'm going to send you. I send a gallon. Does the gallon, is that enough? Can the network capacity hold that? We okay? It's less than 2. That 1 gallon pours into the bucket on the other side. We're good. Dump it into into your receive pool, fill up your bucket again. So we're still okay. Now that went so well. You told me that you got everything that I sent. There was no loss, not even a drop of water went on the floor. So the server goes, you know what? That's great. Let's try 2 gallons. Let's double that thing. Let's try to turn up the volume a little bit. So now we're at 2 gallons of send. This is now where we hit the limit of the network. All right? So we're at our network congestion point. The server, though, many stacks these days, won't stop there because it doesn't yet know that we've hit our head in the ceiling. What's a symptom that we've hit our head on the ceiling and we're going to start losing a few drops here and there? If I'm in a trace file, what symptom am I going to look for that, yep, I hit my head? Packet loss. If I put 3 gallons, shove that down that pipe at once, and say, I know you can only do 2, but you will do 3. What's going to happen? My pipe's going to burst, and I'm going to have water spilling out. A lot of it's still going to get to the other side, but I'm going to have packet loss. Okay? That's my first symptom that I just stretched things too far. So that packet loss or congestion, depending on the TCP algorithm that it's using, if you guys went to Vladimir's session yesterday, I think he's repeating it today, or maybe tomorrow. But anyway, that's all about that congestion window algorithm, how that works, and how some are loss-based, some are congestion-based. But basically, the bottom line is, once I can sense I tipped over what the network's comfortable with, what I'm going to do is say, you know what, my bad, whoops. Let me go ahead and back off. Now, so what we'll do actually on this side is we'll just reduce our send window. Now, the other thing that we need to keep in mind is that at any one time, at any 1 millisecond, at any 1 microsecond, the network can go from being able to handle 2 gallons at once to down to a pint glass. Thinking as network people, what can cause that to go from being able to handle 2 gallons down to a pint glass? What's that? Yeah, competing traffic. We're not the only ones that are using this pipe. This isn't a dedicated line between our swimming pools. In fact, all your neighbors have swimming pools too. They're using this pipe too. So it could be at any one moment, our network capacity, it doesn't stay exactly at 2 gallons. Even if TCP figured out that 2 gallons and everything is just rock star awesome, our network capacity can change. Contending traffic, most of the time that's what it is. It's that congestion. So we only get to use what's left over. Now, depending on the TCP send algorithm in place, that will determine how aggressive we are with our traffic as far as competing traffic. All right, now, let's talk for a minute. These are some numbers that as network analysts, you want to know about your network. If you haven't ever worked out the bandwidth delay products before, let's talk about this for a minute. Let's actually throw some numbers at it. So here we've got our hose. We've got our 2 gallons of capacity. Let's actually turn that into some numbers. Let's just say you had a 1 gigabit per second link, end-to-end. You shot it with iPerf. You know that it's a gig. It's not 445. No, it's exactly 1 gig per second. You've shot it. You know it. You're able to maintain that level of utilization without too much loss. All right? If we have a round trip time of 150 milliseconds, okay, what we want to do is work out how much data can I actually have on that wire. And not just in one direction. I want to be able to send. You actually receive my data, and you are acknowledging that data. I get your acknowledgments before I stop sending. That's my goal. That way we don't have gaps in our send. So we take our 1 gig per second, multiply it by 150 milliseconds. That gives us 150 megabits per second. That would be our capacity. Let's change that to bytes instead of bits We want big B because we're talking about the amount of data, not just the rate that we're sending at. For a 1 gig link at 150 milliseconds of network latency, I should be able to transmit 18.75 megabytes at once. Okay? I want to be able to sustain that amount of traffic. That would be my number, my golden number that I'm working with. There's our bandwidth delay product. Now, let's just say there's our 2 gallons up there, okay? That's our target. When we first start out the TCP connection, again, we don't know what that number is. So let's just say that the receiver gives us a nice conservative receive window. Let's just say it's 65K. Send window, let's start something small. Let's start at 8K. Again, I don't want to overrun my network. Now, let's go ahead and have you open up the example number 1. Let me tell you a little bit about these trace files. And we have 3 sets of trace files. Exercise 1 and 2 go together. Exercise 3 and 4 go together. Exercise 5 and 6 go together. Exercise 1 is the client perspective of a file transfer. Exercise 2 is the server capture of that same file transfer. So what I want you to do is get comfortable with looking at trace files from different perspectives, from both the client and the server. These were all taken in a demo environment. They were actually gifted to us by Mr. Saki. So I really, really appreciate that he did this for us. He said, hey, use these traces because he had them all queued up and everything. If you were in, can I project yet? No? Okay. If you were in the weekend course, you know exactly where the instructions are to start up this lab or start up the exercise. If you were not in that class, then just go up to statistics and go to capture file properties, and you will see some questions in capture file properties that will guide you or ask you leading questions to go through the trace file, okay? That's where you're gonna find your questions to answer. You're also gonna notice, just a quick disclaimer as well, Mr. Saki gave us these trace files, but he wanted to be sure that at the bottom there's a disclaimer, a share license in there. So these are his property, so no one go make $1 million off teaching with them, right? These are his property, so please just use it your own expense. I don't know. Yeah, just use for your own personal use. I did get permission to add the questions and to change the file names, but all right. So here's what I'd like you guys to do. Now that we actually are back, did I have anything else to do? Nope. Power went off right on time. Okay, so I'm going to give you guys a little bit of time, and after, we're going to walk through this example, and what I want to do is just show you some of the tricks that you can use with Wireshark to do some of this analysis and find these kinds of issues a little faster. So your goal, this is just a simple file transfer. You're going to notice if you have, let me blow this up for you. There we go. You're going to notice if you have like a bad TCP, you go up here, you hit bad TCP. Well, there's no retransmissions in this trace file. That's good. So we just added our TCP analysis.flags and no analysis window update. Things are looking clean from that perspective. However, this was a slow file transfer. Our network capacity, he told me he had it set to 100 megabits per second. So we can do the math on, I believe this was a 1 meg file that he was moving across a 100 meg per second link. We can think about how long that should have taken. So here's my question to you guys. On the client side, look through it. What do you think is the root cause, or which bucket would you blame in this trace file? Once you've come to a bit of conclusion, go ahead and open up the server trace file, and then you can validate whether you got that right or not, or if you get any further information based off the server side. All right, I'm going to give you guys 5 to 10 minutes. I'm going to go rove around. You have questions, you get stuck, raise your hand, let me know. Otherwise, I'm just going to let you check this one out for a little bit, okay? All right, let's check this one out. So first, how about, tell me about the throughput. What'd you guys think? What'd you measure it as? 1.8 gig? Okay. Anyone else? What do you think? First of all, are we happy with the throughput? Right? There's a reason why we got called to troubleshoot, right? It was slow. There's a couple of places we can look. One quick and dirty one, it's right there under your properties. What do you see under your properties? If you go to capture file properties, what's your just run-of-the-mill average bits per second? What does it tell you there? He just said 10 megabit. Does everybody see that? Does yours say K? So that's a spot we can head check, but where's another place that we can measure the throughput? Okay, just heard the gentleman back here. He said throughput graph. Did anybody use that? Yeah? Okay, let's just give that a shot first. Now this is a quick transfer. As you can see, it didn't take very long, right? Our whole thing is what, a second here? So yeah, we're under a second. So let's take this graph with a bit of a grain of salt. If we come down to throughput, did everybody see that? I think I went too fast. Here we go. So stats, I come down stream graph. I'm just going to go throughput. All right, I just want to see. Now, the other thing, I also selected a packet going in the direction that I wanted to analyze. Okay? If I had selected one of the acknowledgments, this graph wouldn't look the same. If you accidentally do that, if you go to this graph and it looks like nothing, it could be that you just picked a packet that was going in the ACK direction, not the data direction. Okay? Just something to remember. So if your graph looks weird, first go and try to hit the switch direction. Maybe you just got the wrong one. We can come up here and make sure that our server is actually the one that's sending us the data. All right, so here on this graph, we have segment length. So the size of the packet or that data that was coming across. Sometimes you'll see this and it's like jumping all over the place. That's kind of interesting. We might want to see it if the data size is small consistently. Maybe we have something in the middle that is breaking them up. Or we have an MTU somewhere, or maybe the method that's being used to transmit this data to the other side is doing that, so that's a symptom. But here we got large packets. We can also see we're less than a second, so the amount of time, if this was a longer trace file, we might have a nice little graph that would go up for a period of time and then come back down. But the maximum point that we see on this graph, it says just over 8 times 10 to the 6th. What does that mean? Okay, so 10 to the 6th is, yeah, 10 to the 6th is 1 meg, so we just multiply 8 by it, and we got 8 megs per second. Now, remember what I told you at the start. This is a 100 meg circuit. So right there, we used 8 meg of it for this file transfer. There's one thing to think about. What next? So we measure our throughput. What other interesting things did you see? How about the handshake? What do we notice there? Okay, so our handshake shows us our round trip time, which is 10 milliseconds. Missing the window scaling. Everybody catch that? Let's go into the SYN. Let's look down at the options. If we come down to the bottom and we take a look at our flags. I'm sorry, not our flags, our options. There we go. Okay, we come down here. We can see we have MSS, maximum segment size. We have SAC permitted. And like was mentioned in the back, we don't have window scaling. Now again, what is window scaling? There we go. So instead of working with a pint glass size field, we can say, give me 5 gallons. We can take the receive window, give it a multiplier, and make it much larger, right? So that option is missing. So the client's saying, I'm not doing that whole window scaling thing, forget it. So the number that you see on my receive window is real. And in fact, one gentleman asked me, he said, I saw the handshake, I put in a hard set window scale factor. He went into TCP and he actually gave it one, and it did use it, right? So the hard set scale factor, if we configure that into Wireshark, it'll actually override the handshake setting, which, to be honest, I just haven't had to do that before, so that's pretty cool. All right, so we're not using a window scale, so let's actually come down here. Let's take a look at our calculated, well, this is going to be real as well. I just have calculated window size as a column. So does this guy ever go down? Does it ever go to 0? No? But right away, just the fact that we're not using window scaling, and this number never goes north of the teens, I don't think. So 15K, 16K, what was the largest you saw it? Pretty low, right? Now in this direction, let me see here, I can just, what was it? 15,928, there? Yeah, all right. So if that's the largest window we can receive, there's your pint glass. All right? So yeah, our network was 100 megabits per second. Our network round trip time was 10 milliseconds. So how much can our garden hose hold in this case? 11.6 megabits or megabytes. Did we divide by 8? Bytes? So we have to take, it was 100 megabits per second, right? Let's take 100 megabits per second, multiply that by 10 milliseconds. Divide that number by 8 will give us bytes. That's our product. That's our bandwidth delay. I don't have a calculator in front of me if one of you guys want to tear on that number. But right away, just with that value, we can determine even from the client side that our receive window is way too small. 15K? Nah. Now we can, it's interesting to look at this trace, not just from the client side. Let's actually pop open the server side trace too. Did any of you guys start doing that one just yet? Let's open that one up. Let's go over there. Actually, you know what, before we do, I'm going to show you one other thing. Let's go to, here's a data packet here. I'm going to come up to stats. I'm going to go to stream graphs. Let's go to TCP trace. And I'm just going to zoom in. So from the client side, we can see we get some data coming in. When this line right here starts to go vertical, that's data on its way into me. That's data coming at me. The green above that is the graph of the receive window. So I always want that green line to be above the data. That's my space that I have to work with. I never want those vertical, they're actually little packets. If you zoom in far enough, you'll see they're little I-beams. But I never want those guys to touch the green line. That means that I ran out of receive window. My receiver with the pint glass, I already sent him a pint of data and he's already full. He can't receive any more data. He tells me, stop sending water. My pint glass is full. I know it's small, but it's still full. All right, so I never want to see those lines converge. Let's open up the server side trace and see if that's what happened. Come back and open that. Okay, talk to me. So first, just doing a quick little scroll, what do we start to see right away on the server side that we did not see on the client side? Window full. So first, let's read this. Let's see what this means. Is this the fault? So this is on a packet that is sent from client or server? Server is sending this packet. All right? Wireshark is tagging it as TCP window full. Does that mean the server's doing something wrong? All right. The client can't handle it. So just at first, when we see those black lines and red letters and it looks scary, we can think, oh man, what's the server doing? And I've been asked that, like, here is this trace file, why is my server's window all out of whack? It has nothing to do with the server. It just means this packet that is sent right now is filling the amount of capacity that we have to work with, which is the receive window. All right? So let's just see how we get there. Let's kind of work up to that. If I go up to before where that happens, all right, I got my handshake, I got the get, I got an OK. Server just launches 3 big packets. Those are in flight on their way to the client. I have a column here, bytes in flight. Very nice column to have if you don't have one on a profile. I highly suggest it when you're doing this kind of analysis. Bytes in flight means this is how much data I have outstanding that has not been acknowledged yet. Okay, it's a good way of getting an approximation of how much that server is able to actually put out there. All right, so if you have that, that's nice. Where you can get that on TCP, if you come down to sequence acknowledgement analysis, you'll have bytes in flight. If you do not see sequence acknowledgement analysis, bytes in flight, if you don't see that, it could be that you just have to right-click TCP, come on over here to protocol prefs, and we want to make sure that track number of bytes in flight is selected. It could be that you just don't have that selected, all right? So we can select that, make sure we got bytes in flight. So here we go. So the server has let 3 packets into the garden hose. It's on its way to the other side. Yes, we have an acknowledgement from the other side after 10 milliseconds. It's going to continue to send. We come down here. This is where we start to run into problems. So we have our calculated window side on our other side. I'm getting it at 11,584. Okay, that's the receive window. My outstanding bytes in flight, once this packet goes out the wire, is going to be 11,584. This packet fills the other side. This will fill up his pint glass. I can't send him anything else until I start getting his acknowledgments coming in, letting me know that he's pouring water out of that pint glass. And I can only send what he's poured out into the pool. Okay? This will stop me from sending. That's why I send that packet, but I got to wait. Now, to help us to visualize this, a nice graph, let's go back to our graphs on the server-side trace file. So this is a simple concept, but I like to use traces like this that are easy to break down to help us better understand those stream graphs. So let's have everybody open up the TCP trace graph. Let's go to TCP stream graph. Let's go to TCP trace. And on this side, let's go ahead and zoom in. What do we see here that's different than what we saw on the other side? How does this look different than the client side looked? Sorry, say it again. Nice job. He just said those the packets, right, are my little I bars. What line are they touching? The brown one or the green one upstairs? It's like right up against the green one. In fact, remember what I said. You never want your data to touch that green line. That green line is your ceiling. All right? I can only receive this much. If I go up to touch it, that means there's no space between what I'm sending and what he can receive above that. So here we can see that our data, just immediately, if you had a server-side trace and you were troubleshooting an issue like this, open up your TCP stream graph and look to see, do I ever touch that green line with data? Okay? Does it ever go up and touch that? If it does, then my receive window is giving me a throughput ceiling. My data can't blow through that ceiling. Why? I got a pint glass on the other side. Until he tells me, I got 5-gallon bucket, go ahead and send more data, I can't put any more than that pint glass out on the water, out on the hose. Okay? So fundamentally, this one, bit of a simpler issue, but it can help us to understand these stream graphs. This one, receive side window limitation, it was not using window scaling. That restricted our throughput to 8 megabits per second instead of 100 meg, which we hope to expect on a 100 meg link. Okay? One other graph. Let's go reset. I want to come down here to window scaling. A little more interesting when we actually have a scale. So these are segments, these blue lines, these are segments, and we can see this is actually bytes out or bytes in flight. We can see it crawls up and it hits the green line and it stays up there. So our throughput ceiling is bound by the TCP receive window. I'm going to bring you back here a few times, okay? This is just one example of a throughput issue like this, okay? Before I move off of this example, any questions so far? Feeling okay? This is just a warm-up for you. Get used to some of these windows, get used to some of these buckets, these stream graphs. So now let's look at another example. Let's go ahead and open up exercise 3 and exercise 4, okay? This one was a little bit different. You can get in there and take a look at what you see. Again, what are we troubleshooting? We're troubleshooting low throughput, low bandwidth usage. In these types of file transfers, they're absolutely going to come up to you and say the network's slow, what the heck's going on? So let's go ahead and take a look at that. Start with exercise 3. You have some questions that can help to guide you in the file comments. And then once you finish up with 3, we can look at 4 and we'll compare those. I'm going to go ahead and rove if you have any questions. Okay, everybody, let's chat. So, this was the client side, okay? So what I'm interested in, let's just jump right out the gate and take a look at, we just do a quick little scroll to see how data is moving. If we come to stats, stream graphs, throughput, I'm interested in the throughput here. So we, in the throughput, we go up to what level and stick there? What was our throughput here? Yeah, so someone said 48 megs, right? So 10 to the 7th, if 10 to the 6th is 1 meg, let's just add a 0, right? Go to the next power. So that's 10 meg. Multiply 10 meg by 4.8, that gets us to 48 meg. Are we happy with that? $100 meg link? Depends. Depends on, I mean, it's not, I call this screen punching slow. It's not screen punching slow. But it just gives us an idea of how much of that capacity we're actually using, okay? So let's take a look at how this was different, or what, if any, types of limiters there are on this one. If we go to, this is on the client, right? So yeah, so on the time sequence side of things, let me zoom in a little bit here. So a lot of times, one of the things that slows us down, one of the things that you want to look for when you're looking at that time sequence graph or the Stevens graph or anything is what I call stepping. Okay, so you have stuff, then nothing, then stuff, then nothing, then stuff, then nothing. That nothing is when you're losing time, right? Think of those as air gaps in the garden hose. That's when I have water that's moving through, but I didn't have enough water. I can't send enough at once to fill the whole thing. So I just have to put a pint glass in there. That pint glass of water is moving, but there's a big air gap behind it. So there's a period of time when we're not sending anything. So we're not efficiently using the throughput as well as we possibly could, right? We still have those delays. Now, real quick, what we can do is we can come over here and take a look at drags. And one nice thing about these graphs is we have our little circle there, and we can click on a very specific area. So if I click right here, I can come down, I see 12 milliseconds. Come down here, I see that 12 milliseconds again. Go to the next gap, 12 milliseconds, 12 milliseconds. So about 12 milliseconds is what that, that space in time where I'm not transmitting, that's how long that delay is. All right, so let's think about that for a minute. Let's actually switch to the server side and just see how this graph changed and see what we can learn from that side. Let's close this down. We're just going to jump up to, here we go. All right. Excuse me. You come down to detail. What profile opened? All right, so here's from the server perspective. So we have our SYN, SYN-ACK, ACK. Just curious, are we using a window scale on this one? I'm seeing this and I'm seeing this. Where do I look for that? Handshake, right? So let's just take a real quick look, come down to our options that we are using. Oh, that was on the ACK, not the SYN. Pick the SYN, Chris, come on. All right. MSS, SAC permitted, we got timestamps, no app just to fill in the header, some packing peanuts there, and we got a window scale of multiplied by 8, that's on the client side. The server side comes back, window scale multiplied by 16. Just curious, you guys ever see a window scale that's 0? You ever see that? You might see that. If you ever do, window scale 0, that just means you can go ahead and use window scaling over there. I'm just not going to, because you're not sending me stuff. I'm sending you stuff. So you're just this lowly little client guy. I'm sending you traffic that way. You're not sending anything back to me, so I'm not going to dedicate a bunch of resource for receiving your data. I'll let you do. We can do this window scaling thing. I'm just not going to make a big deal out of it. Okay, moving on. Oh, yep. That means, exactly, that means your little window scale thing that you want to do, Mr. Client, I don't even know what you're talking about. So I won't send you any more than your actual advertise receive window is. So his question was, just for the recording, with the window scale, we need to see that option in both SYNs, right? In order for both sides to advertise that they support that option. That is true. That's one reason why a server might not use an actual window scale factor, but they will put in the window scale there. They're just not going to use a value because the server's like, look, I need a big window when you're sending me data. If I'm sending you data, I don't need to plug that resource up just to keep a connection open. Question?
Is that the same thing with the SAC?
Yes, SAC is this. So if in that handshake, we both have to we need to agree on, well, always be careful with the word negotiated. It's not negotiated. This is an advertisement of what you can support. And if you don't support SAC or know what that is, then I can't do it either, right? Same thing with window scaling. If you don't know what window scaling is and we're not going to use that option in this connection, I can't use it either. We can have differing MSSs. That's just an advertisement of the payload size that you can receive. We can disagree on that. We don't negotiate that. If that MSS, anyone know, just a trivia question, if MSS is not there, speaking of TCP options real quick, if you send me a SYN and it has no options, not even MSS, anyone know what the maximum size packet that I should send you is? Patrick knows. 536, that's exactly it, Patrick, good job. So when in doubt, that is the when in doubt MSS. Now, that said, now that I have said it and I just got recorded, you can probably go find a stack out there that breaks that rule and sends 1416 anyway. But yes, a lot of these are advertisements of what options you can use throughout the connection. All right, so in this example, I'm just going to pick a data packet. I'm going to go up to statistics. I want to come down to stream graphs. And let's just start with TCP trace just to have fun. Let's go into zooms. Going to zoom in again. What behavior do we see here in this trace? We see stepping. And what thing do we never want to see, especially on the server side? What line are we touching? That green line represents what? Receive window. So on the client side, that is the amount of space above the present sequence number that I have in my TCP receive window. All right? So right now, I can just look at the TCP trace graph. Not only do I have that stepping thing, that means I've got these pauses, but the reason for those pauses, I send and I have to stop because I have touched that receive window. In fact, as soon as the client, let me zoom in a little here, even a little bit more. As soon as the client sends these acknowledgments, he's increasing his receive windows, or rather the receive window is giving me space to transmit, if even at one packet at a time. Right, so these ACKs are coming in and letting me know I have a little bit of space, a little bit of space, a little bit of space. So that server's saying, great, here's data, here's data, here's data. Then we have suffer a round trip, and then here's some more data, here's some more data. So we're hitting our heads on that receive window on that side. Now we can see that if we scroll down a little bit. We see where this starts to take shape here. Here's our bytes in flight, our receive window. Let's come down to bytes in flight, right around here. Right around here. So packet, if you have those values, about packet 331, the sender, for me, I've got bytes in flight. So I can see I've got 123.243 in flight. The receiver has 124.328 total window. That's how much can be outstanding. Now these two numbers, if they're ever equal, if they're ever the same, that means that my bytes in flight has hit the ceiling of the receive window. In this case, though, I don't see those black lines with red letters saying receive window full or TCP window full. Why is that? On the last trace, I saw those black lines. Window full, window full, window full. How come we don't see that here? Bytes in flight, you see I got 123.243, 123.243, right? What's the difference in these two numbers? Let's take 124.328 and subtract 123.243. Could someone do that real fast? 124.328 minus 123.243. Who could do that real quick? We had someone in the class over the weekend that was just boom. They had the math down. What's that number? What is it? 185? So I'm telling, is that it? 185? 1185. So basically the client is saying, I only have 1185 bytes left before I hit the top of my window. So I am almost full. The pint glass has a shot glass worth of space up there. Because it's basically I'm saying that's all the space that I can receive. The server's saying, okay, great. All I can do is send you a shot glass at a time. Okay, here's 2 packets. But the reason why we don't see that black line is because we don't actually completely fill the window. The server wants to be efficient, right? So you can see all of these packets are my maximum segment size, 14.448. So at no point does the server say, you know, this is all you've got for space. Let's go ahead and drop the MSS a little bit. Let's go down a little lower and just completely fill you up. That's not an unusual behavior to see on a server. If you have a lot of data to send, the server would rather send it out at the full MSS rather than stop, give you just a chunk of one of those packets, and then keep going full MSS. Instead, you'll see that behavior. As soon as I say this, you'll find a server that behaves differently. But a lot of them want to use that full MSS size. That's why we're not completely filling the window, but we're going as full as we can with full packets. The math isn't falling right on that line. There's a question.
Yeah, Chris. Is this telling us that the window scaling up is not big enough to handle the transfer, or that the client's not fast enough in the buffer?
It's a great question. The question was, is this telling us that the scale factor is not big enough, or that the client is not fast enough to receive or to use a larger window? Depending on the application, I'd have to go and see what exactly the application and operating system was. But in this case, that's exactly it. The client wasn't using a large enough window to fill the network. Could have been this was an old crummy stack that needed updating. Could have been that it was an application that was overriding the OS stack and saying, use this feature when you use this application. So yeah, this was definitely receive side. Simply was not using a window size big enough. I know we've seen different options like within Windows, like receive window auto scaling. You've seen like different features like that start to come out to address things like this, to give that client the ability to go much higher with its receive window. All right, I got one more example for you guys before we, see what happens. All right, let's go ahead and open up exercise 5 and 6. While you're working through it, I'm going to take you through it. This was exactly the same type of scenario. You got a client, you got a server, but this time you have exactly 0.1% packet loss. You heard me, 0.1% packet loss. Okay, so go ahead and open up the trace. You can start client side. Take a look at where those retransmissions happen. You can watch TCP try to recover. While you have that open and you're looking at it, I just want to talk to you a little bit about that send window when we see loss. So you can go ahead and open that up. I'm just going to go straight to the server side of this one. Okay, this was 0.1% packet loss. And what I'm going to look at here is my bytes in flight and my window size. If you open up exercise 6, you can just follow along with me. I'll just talk us through this since we're running out of time. So here we have our window sizes start small, but if you notice, go ahead and let your eye take a look at that window size. You notice that our window size is climbing on the client? 95K, 101K. I'm just looking at this number here, and it's growing. 121, 121, 121. Well, the server is like, whoa, you got a window size that's climbing here. Well, at first, we can see that the server just wants to put out 21,720 at a time before it sees more acts come in. I still have a ton of space to work with here, so I'm not super worried. What I'm interested in is how big does that receive window size get before we see our black lines with red letters. All right, you can see over in my intelligent scroll bar that I'm about to run into some packet loss. This is where we hit our head on the network throughput capabilities. I either hit congestion, or I hit an FCS error or some other type of link level error, and I got a retransmission. All right? So let's just look at how the transport, the throughput looks before that loss and after that loss. All right, so I'm just interested in my receive window coming up on that loss. Whoop, I just jumped over it because I scrolled too fast. Okay. So here we are right before we have some dupacks. we have a point of loss. The client is coming back and saying, hey, buddy, there was a gap in the sequence numbers. I was good to here, there's a gap, and now I'm doing my dupe-back thing with my selective acknowledgement. So I'm able to continue to act left edge, right edge, let this grow. But I'm going to let you know, back here, this gap of sequence number is what I need you to retransmit. Right before that period of loss, my receive window on the client side is 121.342. We notice the bytes in flight from the server's perspective. We hit 40K. We had 40K outstanding. All right, so that's how much it put out before we saw something happen. All right, let's see what happens after this. Let's see after this clears up, we get our retransmission. Okay, we can see here, we had a total outstanding 57. We notice what happened after the point of loss. This is the server again doing bytes in flight. So on the server side, we were up in the 40s. We hit our head on some type of ceiling. Our bad. Didn't mean to go that fast. I thought we had a 10 gig network. We probably have a drinking straw between us. We're going to go ahead and reduce the congestion window down, and it actually looks like it cut it in half. It was at 40 something up there. It sensed loss, and it went down to 20. So right there, we just pulled our brakes. After that point of loss, this is where things get interesting. We can start to see how the congestion window works. Check this out. So I'm actually going to set a timer over here. I'm just going to say set unset time reference. So, okay, we have 2272 outstanding on the wire, all right? Notice when this number changes to 21720, this is another full-size packet more. So we were putting 2272, that 18, let's forget that for right now. But just at this point, we went ahead and added another packet, another MSS of collision window. So collision window, or I'm sorry, not collision, congestion window. Collisions is a whole other topic. Congestion window is a function of adding, it's a number where I send a certain number of MSSs, maximum segment sizes, out at once. Once I hit congestion, depending on the algorithm in place, I'll knock it back. In some cases, I'll go all the way half to what I was before, and then I will add additive increase for especially these older stacks. I'll add one MSS for every network round trip time, and I'll only add one MSS. So every 20 milliseconds, all you get is one more MSS of collision window. That's what's happening here. We had 2272. You notice over here the stopwatch that I started? I started a stopwatch when we first saw that 20. Now 21 milliseconds down, I think the network round trip on this trace file is 20, right? Okay, in the handshake. 20 milliseconds later, I add one single MSS to my bytes in flight. That is exactly one more. All right? So let's see when that started. Let me right-click again. Let's go to time reference. I'm just going to zero my counter out again. What I want to look for is when does this bytes in flight go up one more packet? Let's scroll. Oh, it just did it. 23,168. We just added one more MSS to our congestion window. If we come over there, all right, 44 milliseconds. So it took twice the round trips just to add one more MSS. Okay? I can go through that over the break a little bit slower if you need me to. That's not a problem. But this is the problem with TCP right here. In some implementations, and especially older congestion avoidance algorithms, they aggressively try to hit that network and send traffic out. But once we hit our heads on throughput, we back down so far that it takes us forever to get back up to what good throughput should be. I actually have a screenshot I wanted to show you. I couldn't share the trace file, but it's just a screen. Bummer. Hang on. I know, guys. It's almost time. Of course, I can't find it. Oh, wait. Yeah. Oh, wait, no. Yeah. Here you go. So here's just here's like an old crummy stack. that was using a long fat network, so a network that had a lot of capacity and high latency. Long fat network. So you have a lot of pipe to use, and it's also a lot of time. That means that your windows have to be huge, and if we have any loss, this congestion algorithm was taking a long time to recover. So this is what happens on long fat networks. When we hit that throughput window, or we lose a packet, when we hit that congestion, recovering from that can take so long that that can really lengthen the amount of time it takes to move a file. Guys, I gotta probably have to stop because we have a break and we have to go to the next sessions. Anyway, if you guys like this, just to wrap up, my goal was to give you guys a bit more hands-on with congestion window. Instead of just going to a session where I just blow a bunch of numbers at you, actually give you hands-on and see how this works. Keep practicing with it. Keep getting comfortable with how sequence numbers work and so on. Please fill out the feedback if you go on the app, and make sure to go ahead and write in if you like the session or not, or come up and chat with me. Appreciate you guys coming today, and I'll see you around SharkFest.